Welcome back. So in problem 6, we have to use complex variables to evaluate the real integral given where p squared is less than 1. So to evaluate such an integral, the first step is to change the given integral in terms of the variable z. And then next step, you integrate the resulting contour integral on a unit circle. And that integration is carried out by determining the poles of the function in terms of z, and then evaluating the residues at the poles within the unit circle, and get the sum of all the residues within the unit circle multiplied by 2 pi I. That will give you the solution to the problem. So this is what I mean. So solution, we have the integral 0 to 2 pi d theta over 1 minus 2p sine theta plus p squared. So this is the same as integral from 0 to 2 pi d theta over 1 minus 2p, but where the sign you put e raised power I theta minus e raised power minus I theta divided by 2I, then you add p squared. So we have replaced sine theta by its equivalence in terms of exponential. So the next step, at this point, we have integral from 0 to 2 pi, then the theta. So factor out 2I, and then we'll have 1 minus p over I into e raised power I theta minus e raised power minus I theta plus p squared. Next step, you see when you multiply this part, so minus p over I, if you multiply by negative I times negative I, so this will give you negative I times I is 1, so negative, negative, positive, so this will be pi. So this integral will be integral 0 to 2 pi d theta divided by 1 plus pi into e raised power I theta minus e raised power minus I theta, and then plus p squared. So it tells us that this is the same as integral from 0 to 2 pi of the theta, and then here we have 1 plus pi e raised power I theta minus pi e raised power negative I theta plus p squared. Now let's call this one just integral I. So you say let z be given by e raised power I theta. So it means the z is I e raised power I theta, the theta, and because e raised power I theta is z, so this is I z the theta, and that implies the theta alone is dz over iz. So z raised power e z raised power negative 1 equals to e raised power negative I theta. Is the same thing as saying e raised power minus I theta is 1 over z. So this implies our integral I will be the integral. Now, when we change into the variable z, then we use control integration. So we put c. So we'll have one plus pi. So this is z minus pi over z, this place, then plus p squared. Then the theta is dz over iz. So which implies I, then you specify where C is a unit circle. So C is the unit circle, not a unit circle. Now, integral along C. So multiply this by every term, so we'll have dz. So iz is multiplying every term here. So I'll have iz. I times I is negative 1, so minus p z squared. I times minus I is 1, so this will be plus p. And then this plus p squared I z. So on rearranging, we have I is the control integration dz. So start with this one, so minus p z squared. Those terms in p, those terms in z, we have this and this one here. So we'll have plus I p squared z, and then plus zi, this term here, and then plus p. Now let's see here, minus p z squared plus ip squared z plus zi plus p. Common here is p z. So I'll have so this can be factorized as okay, we can just write it as general quadratic, which is minus p z squared plus ip plus I. So this ip squared plus I z then plus p. So product is minus p squared, sum is ip squared plus I. So the numbers will be p I. Okay, so we have without going into that, we can actually just say this p this denominator can be rearranged as I is integral along C dz divided by iz plus p, and then multiplied by izp, then plus 1. Hope you can see that this is what is happening. So common here between these two terms, we can say factoring out izp into, so here I need zi plus p, and then plus 1 into zi plus p, so that I have izp plus 1 times zi plus p. So this is the factorization of this denominator. So that's why we have from this term to go to this term. So factoring out izp for these first two terms, then this is what you get in the first bracket, and then same thing at the second bracket. So thus our I integral is given by dz over iz plus p times izp plus 1. So here, f of z is given by, remember we have specified that c is the unit circle, 1 over iz plus p, izp plus 1. So immediately you have the f of z, then find the poles. Poles are taking the denominator, equate to 0, i.e. iz plus p times izp plus 1 equals to 0, which means in the first case, z is equals to p over I, and in the second case, z the same as negative 1 over IP. So remember, this is a negative because you have to take this one to the opposite of this sign is plus. Now you can rationalize or multiply by the conjugate, then multiply by the conjugate. So this will give us 1, and then negative, negative, positive. So z is pi, and z here will have I over p. But we know that modulus of pi is the same as p squared, and modulus of ip the same as 1 over p squared. Now, since p squared was given to be less than 1, this from definition, then pi, which is equals to p squared is less than 1, is the only pole within the circle. This is what I mean, that if p squared is less than 1, then it automatically means 1 over p squared is greater than 1. So this value here, I over p, will be a pole outside the unit circle. So let's find the residue. So residue at z equals to pi will be given by limit as z approaches pi of z minus pi times f of z. This is how we find residue. Then f of z is iz plus p. So we say this is the same as limit z approaches pi z minus pi. F of z is 1 divided by iz plus p times izp plus 1. So this is the same as now remember here, this is z minus pi. So if I multiply this one by negative, I have limit as z approaches pi of z minus pi divided by I z plus p, and then izp plus 1. So I can, if I multiply this one by negative, I multiply this expression by negative I. So I multiply the numerator by negative I, denominator by negative I. Okay. If I factor out negative I in this term here, I'll get limit z approaches pi. So this is z minus pi. So here I factor out I. So I need to have z here. And then I need to have minus pi. So that when I multiply this by this one, I'll get minus p times I squared. So I squared is -1. It gives me back my original plus p. Then this minus ip plus 1. So by doing that, this and this cancels out. So I get limit z approaches pi of 1 over I into izp plus 1, which will be 1 over I into ip times pi plus 1. And that will give me 1 over I into I times I is -1, so minus p squared plus 1. So this will give me 1 over I times 1 over minus p squared plus 1. So that's the residue of the function at the pole pi. So By Cauchy residue theorem, I is given by 0 to 2 pi d theta over 1 minus 2p sin theta plus p squared is given by 2 pi I times sum of residues within C, the unit circle. Because we just have one, so we'll have 2 pi I times 1 over I times 1 over minus p squared plus 1, this value here. So you see, by doing this, I and I cancels out. So we'll have 2p 2 pi over minus p squared plus 1, or we can write the integral from 0 to 2 pi d theta over 1 minus 2 sine 2p sine theta plus p squared is given by 2 pi over 1 minus p squared. So this is the solution to our given problem. Thank you.